So last time we talked about how to detect error in a data qubit, and I mentioned several names about the measurement qubits and syndrome measurements. So they are all commonly used names, but you might see this type of keyword many times if you search for the quantum error correction. So syndrome measurement. So what is syndrome? So you have a symptom in your data qubits, and you want to detect the symptoms without changing the state. So that's what the syndrome measurement means, literally. And so there are two types of syndrome measurement. There are only two types of syndrome measurements for any kind of quantum error correction. So either X or Z. So X syndrome measurement gives this circuit, and that syndrome measurement has this circuit. And the last time I kind of tried to give you the idea what is going on, and I made a hiccup. So let me modify a little bit. So whenever you take a syndrome measurement, you have to initialize your measurement qubit. So the first register is the measurement qubit, has to be initialized to be 0. So it's very easy to initialize your quantum state in either 0 state or 1 state. So for example, in a light's case, so you just pass the light into filter lens, so you get a +0 or -0. Or if it's if it's an electric spin, then you just give your magnetic field in a certain direction to initialize your quantum state in the 0 state or 1 state, whichever you want. But of course, there is an error. Once you initialize, you think you initialize your quantum state, there could be an error again. So you never guarantee whenever you do something on your quantum state, you never guarantee that the quantum state stays the same. But what we want is we want the error detect on the data qubit, which is the second register. So we assume that there is no error on the measurement qubit. So in the real life, of course, there is an error correction. There is a chance of error on the measurement qubit and data qubit, same. So we kind of simulate how much the error detection could be valid, what percentage of your error correction result could be trusted when you do this kind of error correction, because the measurement itself could be errored, right? So anyway, so what I'm trying to emphasize and make up my mistake the last class is that whenever you try to measure or passing your state into the syndrome measurement, you have to initialize your measurement qubit into 0 cut state. So then, once you pass this, whatever the data qubit was after the measurement, so here you have to finish with the measurement here. So the data qubit goes on forever. So this is just one block that you apply to data qubit with this measurement qubit. But in the measurement qubit, the circuit ends here. So whenever you hit the measurement block, it's the end of this quantum circuit, right? You have to restart the new quantum circuit. So every time you take an error detection, your measurement qubit is used up. So no longer is used after this circuit. So that's why we also have to, that's another reason why we always have to initialize the quantum state into 0. So, right? Okay, so we did lots of computation. And today we're going to talk about 2 early quantum error correction code, and which is sometimes called STIN code, which is 5-qubit code and 7-qubit code. So 5-qubit code. So what is it? So whenever you try to use the quantum error correction, what you're doing is making a code that detects an error and also encode your physical qubit into logical qubit. So 5-qubit codes encodes 5 physical qubits into 1 logical qubit. So what is logical qubit? So logical qubit is kind of a abstract qubit. So it's just as the description indicates, it's collection of information stored in several physical qubits, but it delivers one one unit of information as a qubit. So I'll show you what that is. So here we have, so I need to draw 9 lines here. So let me start from bottom here. 1, 2, 3, 4, 5. Okay. So here I have a, let's label it here, 0, 1, 2, 3, 4. So 5 physical qubits. So this is quantum circuit, but let's pretend that we have a 5 qubits here. And there's something going on. We're going to store some information in this 5 register. So initialize as 0 in the first place. And so let's say this line, the length of this line indicates the time duration that you pass from one point to another. So you hope that your zero cat state is preserved at the end of the time as 0, but it's not happening. So we want to do something to detect an error occurred in any of these, and we also want to find out which kind of error occurred. So these are physical qubits. So 5 physical qubits, and there are 4 measurement qubits for the syndrome measurement. So 4 measurement, and measurement qubit, and there are. So I don't think I can draw all of them. There are 4 type of circuits. So I'll just draw one type of them. So so first of all, let's see, 0, 1. So we have, so here we always initialize with Hadamard. And okay, so let's label it as 0, 1, 2, 3. So on the zeros measurement, what's going on here is we're going to put Control Z here and Control X on the second and Control X on third and Control Z on the fourth. So here at the end, put the Hadamard back here. So so I only showed you the one type of measurement qubit, so 0 measurement qubit. The other measurement qubit is not doing any work. So I don't have space here, so I just give one example, and then I'm gonna lay out the detail for other measurement qubit. So what does this measurement 0 qubit does? So it detects the eigenstate of these 4 data qubits based on Z measurement, X measurement, and ZX and Z measurement. So we're gonna call this measurement circuit as M0 equals to Z1, X2, X3, Z4. So what it really does is that, so I can combine this. So I can combine this part. I can combine this block in as M0. So just pretend that this M0 is a quantum circuit that acting on the 5-qubit state. Okay. Then I can say, now I can draw only the, let's see, 4 measurement qubit, 0, 1, 2, 3, and here we have special physical qubit, the data qubit here, and so here this is initialized as zeros for the 5 qubits, and the red part I just draw here. Sorry, so red part is actually not containing the control part. It's only this part. So it's same as applying ZXXZ in this sequence whenever we have this control activated, right? So this is the measurement 0 qubit, and whenever it's activated, we apply that ZXXZ in that sequence on the data qubit register. So I'm gonna give you, so you see what I mean? The red part, the red block right there, here, is exactly here. So this M0 here, okay? So let me write down 3 more qubits, the gates here. So M2, X3, X4, that's 0, M2, that's 3, X4, X0, that's 1, M3, that's 4, X0, X1, and I think I made a mistake, Z2, I guess, Z2. So these other 3 qubits are attached to the next measurement qubits. So we have M1, whose control is attached to the first data measurement qubit, and M2 attached to the second, M3 attached to the last one here. Okay, so again, the measurement qubit is always initialized at 0, and so this is just the name. So let me just erase the name, and at the end, we always finish our measurement qubit with the measurement. Okay, so here's the measurement. Okay. So let's see what happens when we have an error. So what kind of error do we have? So we could have an error on these 5 data qubits. So each data qubit has X error or Z error. So Xi, Zi to be the X and Z error occurred on physical qubit, or in other words, data qubit I. Okay, so let me draw a big table here. So here there is a case when X0 occurred. There is a case when Z0 occurred. There's a case X1 occurred, Z1 occurred, and so on, right? So let's do it here. So and then, so after taking this circuit and take a measurement on the measurement qubits, let's say, so here, if I could make it a little bit better. Let's say the read-off of this measurement qubit is C0, C1, C2, C3. Okay, so I'm gonna see what's the measurement outcome of each measurement qubit. C0, C1, C2, C3. Okay. All right. So let's pretend that we have X error here. And okay, so before we actually start to detecting the error, we have to initialize our quantum state in the data qubits as eigenstate of these measurement qubits. So, let me write down the steps here. So first, let me write down this title here. So how 5-qubit code works. So first, you take initialization. So initialization means that you first want to run this circuit all once, and then take a measurement. So at here, so what happens when you run this circuit, for all 4 measurement qubits? So what's going to be the measurement outcome here? So let's think about first measurement qubits here. So measurement qubit 0, it's detecting it's containing the Z syndrome measurement on the first data qubit and so on, like this. So whenever you take a measurement here, it's going to stabilize. It's going to make your data qubits, all data qubits, into eigenstate of these gates, of these measurement gates. So look at this Z1. So look at this Z1 here. So don't think about others, control qubits here. So you can think of this as a successive operation of the syndrome measurement. So first, you take the syndrome measurement on this first data qubit with the measurement qubit on zeros here. So after taking a measurement, whatever that outcome is, your first data qubit will be eigenstate of that syndrome measurement, right? Eigenstate of that syndrome measurement is either 0 ket or 1 ket, right? So this could be just initialized as it is. And then what? After taking this second one, you get second data qubit stabilized or initialized as the eigenstate of X syndrome measurement, which is plus ket or minus ket, and so on. Okay? So after taking, because you can think about this as a H, 2H in between these 2 control qubits. And this syndrome measurement gives the initialization as an eigenstate. This one also initializes as an eigenstate, but 2 H's in a row will be just identity gate. So you can just ignore this and think about this last and front Hadamard gate. So anyway, after applying this, your data qubit is initialized as eigenstate of all the syndrome measurement, right? So that's what the initialization state does. So take, run the circuit and measure the measurement qubit. Now, and then, so we're kind of learning the code itself. So let's assume that there's no error in an initialization state. So if there's an error in the initialization state, it gets really complicated. So assume no error here. Okay. So now we begin our error detection. So how do we detect error? So now let's suppose that we have X0, which means that we have X error on the qubit 0 on our physical qubit. So what happens then? So here we had error, X error. So in the measurement qubit 0, the value is not changed at all. So we assume that initially that all the values is 0 initial. It was 0, right? So if there was no error, it has to be always 0, right? But let's say we have error in here, but error in here has nothing to do with this measurement gate because it's applying to the qubit 1 to qubit 4. So it will be just the same 0 here. So look at the measurement qubit 1 here, the label 1. So this one consists of these 4. So it means that Z detection at 2, X detection on 3, X detection on 4, Z detection on 0, right? So if there was X error on the 0th qubit here, then since it's a Z syndrome measurement, it detects X error, right? So syndrome measurement, if we have Z error somewhere in between this quantum control gate, then it changes the measurement outcome into opposite, right? So since it was originally 0, it will change into 1, right? And what? So look at the third one, the M2 here. So we have Z3, X4, X0, Z1. So now you know that we don't care about on other qubits. We only look at whether the error syndrome measurement is attached to the 0th qubit because its error is on the 0th qubit. So X error, this is X measurement gate, right? If you have an X error, it cannot change the measurement outcome because the quantum state is already stabilized as an eigenstate of X. Applying X just makes this quantum state the same because it's a +1 eigenstate initially. So it doesn't change. C2 is also not changed. How about C4, C3, so M3. So it still also have X0 here, right? So it's not changed at all here, right? You see what I'm saying here? So it's about whether your measurement outcome is changed. So initially it was 0, so if there was no error, so that means no error means no quantum gate is applied, no unwanted gate is applied. So you can say that identity gate is applied. So in other words, I is the case, then it will turn out to be 0. But when X0 is applied, then it will change it to 0, 1, 0, 0. And we can detect it by taking a measurement. The measurement outcome will be exactly 0, 1, 0, 0, right? So what happens when Z0 occurred? So you have to go for X0, right? Where is X0? X0 is here and here, right? So that's the only case you can detect the change, these two. So C2, C3 will change it to 1 and 1, right? And what if this X0, Z0 occurred at the same time? So let me do one more before we move on to the qubit 1. What happens when the X error and Z error occurred on the qubit 0? So we call it Y error. So you see Pauli X, Pauli Z multiplied together to get Pauli Y with some constant factor. So the constant factor is changing the phase of the quantum state, but it changes the phase of ket 0 and ket 1 at the same time. So there's no phase difference between ket 0 and ket 1. But when you're looking at the measurement outcome, since we are talking about the decoherence on the phase difference and the bit flip, we only need to, we can just say these two errors is actually same as applying the Y gate on the same qubit. So in that case, what? So you can say that this is actually, let me write more, so kind of X and Z0. Okay. So in that case, you can see that it's 1, 1, 1, right? Because this is not coincidence. So we don't have no overlapping here. So how about X1 and Z1 and Y1? X1, let's do it again, do it together. So in X1, you go for Z1, you just look for where Z1 is, all right? So 1, 0, 1, 0. That's where I can see Z1. And how about Z1 error? So you have to go for X1. Where is X1? x1 is on the end and not else. So this is the case. And y0 is this. So let's do all the way up to 4. So extend this table and x2, z2, y2, x3, z3, y3, and x4, z4, y4. Okay. How about x2? Just give me the 0 and 1s. So where do you see z2? 0, 1, 0, 1, right? z2 is here and here, right? How about z2? When you have a z2 error, you go for x2, right? So where is x2? Only the first, right? So 0 here, and y is this. And how about x3? You go for z3. I can see z3 only at the third one, yeah? 0, 0, 1, 0. And z3, you go for x3. x3 on the first two, so 1, 1, 1, 0. 0, and y3 is 1, 1, 1, 0. How about x4? x4 is for z4. Where is z4? Top and bottom. And z4, you go for x4. Where is x4? Middle two, right? 0, 1, 1, 0. And y4 is 1, 1, 1, 1. Now, so we have a kind of the array of zeros and ones, right? It's kind of a stamp your footprints after taking a measurement on measurement qubit. Does any of these footprints coincide together? Do you see any of these two footprints occurred twice? So can you see 0, 1, 0, 0 anywhere else other than this? So I don't think so, right? There's only one here. And how about 0, 0, 1, 1? So I can't see anything else, right? So anywhere else than here. So you have how many footprints on this part? 15, right? So there are 3 types of error. So if you consider y error as a separate type. So there are 3 types of error on each qubit. There are 5 qubits. So there are 15 kind of error you can detect. And there are 15 footprints assigned for each type of error. And there's actually one more footprint, which occurs when there's no error, right? So there are total 16 footprints, and this 16 is exactly the number of the footprints, number of array of bits with 4 bits, right? So what does this say? If you use this quantum 5-qubit code, you can find X and Z error separately. That's the important part. So X error and Z error could be detected independently on each physical qubit. But there's one condition. It can only detect an error when it's occurred at the single data qubit, right? So what if you have X error occurred on the qubit 0 and qubit 1? So then it kind of mixed. So here, X error makes this measurement turns into 1, and X error on the data qubit 1 makes this one and this one turn into 1. So overall, if you have these 2 errors, it could the footprint, the read off will be 1, 1, 1, 0, right? Look at these two, 1, 1, 1, 0, right? But there is 1, 1, 1, 0 right here, 1, 1, 1, 0. So you have the same footprint for 2 situations. One is you have X error on the qubit 0 and qubit 1. The other is you have Y error on the qubit 3. So you don't tell which one is actually the case. So this quantum error correction code can only detect one error in a 1 qubit. Okay? So if there's error on more than 2 qubits, it's actually not working. It's not right to use this 5-qubit code. Here, use the table. find on error x, y, z on a single qubit. That's the case. Okay. So again, what happens when you after you detect a detection? What happens when you detect an error? Okay. So you don't modify the error. Okay. So that's the important part. So so what actually happens when error in the quantum error correction is that it's actually not correcting error. So let's say you're supposed to get an result which is 0, 0, 0, 0. Okay, but instead you kind of get, let's say, 1, 1, 1, 1. Okay, so then you can imagine that, okay, so there must be an error. I know that error occurred during this time, so the circuit is quite larger than this one. This is only one block of your circuit, and in this one block you take a measurement whether the error occurred, and you move on. After taking a measurement here, we didn't change any data qubits here, so we kind of say, okay, so there was an error, Y4, somewhere in here, the error occurred, and then you move on, right? And then after all, you got some result, and you kind of recalculate as if you throw in your error as an unwanted gate. So, and then you kind of going back tracing your calculation, if the result was actually, if the supposed result was otherwise, if there was an error, if there was no error. So just error detection and collect result, not changing the quantum state. On data qubits until the end of this circuit. Not just this circuit, the entire circuit. Okay. So the best way is you just take the error correction or error detection circuit after each block. So for example, you have X gate applied to your logical qubit. You have X gate on the logical qubit. And then you take the error detection block because you don't know whether the error occurred during the application of X gate on your logical qubit. And then you do some more quantum gate operation on your logical qubit, and then take a quantum error correction block. And then after your computation is over, then you backtrace you collect the results of error detection, and then you kind of backtracing your error, your quantum circuits, and then calibrate your final result, assuming that there was kind of unwanted gate applied to your circuit. So that's kind of error correction, how error correction works. So this is basically error detection part. And before I move on to the logical qubit part, because we want to talk about logical gate and logical qubit. Any questions on this part? Yes. No. So you can switch the order. It doesn't matter. So that's how they designed the circuit here. So here you don't have two gates on a single qubit. Every gate in each of these have different qubits, right? So it will be a problem if you have the Z gate and X gate on the same qubit happening in one qubit block here, but there's none. So you can switch the orders. And you can actually switch orders of everything here, right? So there's no overlapping. Any other questions? Yes. Yes. No. So So originally you can, you don't have to start the data qubit with the 0 ket. Just, it will be just random state, right? And then let's say you run this circuit once and you take a measurement. And based on your measurement, your data qubit will be an eigenstate of this measurement qubit. So what does that mean? It's kind of complicated, so I cannot give you the exact quantum state in a ket state, in a ket notation, but let me give you this example. So there are how many? So if your data qubit is initialized at random, and then you run this circuit, not this circuit, sorry. So this circuit once, and then you read off the measurement outcome here, and suppose that you got 0, 0, 0, 0. So it means that your quantum state on this 5 qubit state, on 5 qubit data state, is initialized as +1 eigenstate for M of 0, +1 eigenstate for M1, +1 eigenstate for M2, +1 eigenstate for M3. So think about this simple case. So I think it's good to have an example before we move on, because I think you have to do it once in your life here. So we have X and Z. Well, maybe now you don't have to do it. Anyway, so let's do it here. So it's a very simple calculation. So say this is your measurement qubit, and you take a measurement here. And when you take a measurement, your data qubit, the data qubit consists of 2 qubits, will be initialized according to your measurement outcome. So let's see. So let me give an example. So let's say this one is alpha 0. Let's say this alpha 0, beta 0, 1, and alpha 1, 0, beta 1, 1. Okay. So then initialize 0 here. And suppose that C was 0. And let's see what happens on the 2 data qubits here. So here we have 0 and 1, 2, 3, 4. Okay, so at the beginning, the size 0 is what? It's getting complicated, but let's do it at least once. So alpha 0, alpha 1, 0, 0, alpha 0, beta 1, 0, 1. And beta 0, alpha 0, 1, 0, beta 1, alpha, beta 0, beta 1, 1, 1. And let's put the measurement state at the end, 0. So that was the initialized state. And after taking Hadamard, you just change the last one to plus ket, right? And then let's think about the first quantum state here. So you only changed X and Z, right? Ket 0 and ket 1, right? So I don't think I have to expand right here, but I already did it. So let's see what happens. So alpha 0, alpha 1. So whenever, okay, so yeah, the same thing stays for 0. Let's try to not to think about the coefficient 1 over square root of 2. And then when it's plus 1 ket, what happens is you want to switch the X and here. So this yeah, this is 0 and this is 1. So you want to switch 0 and 1 here, right? So alpha 0, alpha 1 is not 0, 0. It's now 1, 0, right? And I think I have to write it longer here. So psi 2, let's see, alpha 0, alpha 1, 1, 0, and alpha 0, beta 1 is now 1, 1. And beta 0, alpha 0 is 0, 0. beta 0, beta 1 is 0, 1, right? So now let's apply the Z syndrome measurement here. So psi 3. In this case, so here it's not changing at all again, right? So because it's 0 here. So now we're changing the qubit 0, which is on the right side. And the only change is when it's ket 1 to the negative. So we have same thing for 0. And here we have alpha 0, alpha 1, 1, 0, minus alpha 0, beta 1, 1, 1. And we have beta 0, alpha 0, 0, 0. And here also changes the sign. Beta 0, beta 1, 0, 1 times 1, right? So, and then Hadamard. So psi 4, the same thing, plus, and these thing, minus. And let's see what happens. So I don't think we have to assume that C is 0. So we'll see what happens for every case. So let's first collect all the cases when we have 0 ket. So we're going to have a 0 ket here and 0 ket here. So just adding these part and that part. So we can see that 0, 0. So what is it? Alpha 0, alpha 1 minus, I don't know, yeah, minus 0, 0. No, it's not minus. Yeah, plus, right? Plus alpha 0, beta 0. Beta 0? How can I get the beta 0 here? I think I made a mistake here. So somewhere in alpha 0, beta 0 cannot be multiplied. So let's see. It's a beta 1, right? It's let me see. So here, this one is 0, 0. Yeah, that's okay. So and then 0, 1. It's okay. So sorry. So I made mistake here. So we have 0, so alpha 1, beta 0, right? And then this is 1, 0. So 1, 0 here. So beta 1, alpha 0, and 1, 1 is beta 0, beta 1. Okay, so now I have to change this a little bit. So this one, alpha 1, beta 0, and beta 1, alpha 0, and beta 0, beta 1. Yeah, so, and then let me just modify this a little bit here. 0, beta 1, beta 1, 0. Okay. So what I'm trying to do here, if you get confused, is what was I trying to do? So I want to answer the question whether I should initialize our data qubit into ket 0 state always. My answer is no, you don't have to, unless you take a measurement of at the end before just before finishing the initialization state. So we'll see what happens when we didn't initialize our data qubit into 0 ket, which is just random state here, and what happens when you take a measurement. So we went up to psi 4, right? Now let's make it clean. So 0, 0, so when it's 0, let's collect 0, 0, alpha 1, and 0, 0 here. So it's alpha 0, beta 1, right? So 0, 0. And then 0, 1. Where is 0, 1? So 0, 1 over there, alpha 1, beta 0, and 0, 1 here. Beta 0, beta 1, okay, 0, 1. And then 1, 0, 1, 0 here, beta 1, alpha 0, 1, 0, where is it? Here. I have to be careful about the negative sign, so I have to go for here, right? So 0, 1. 0, 1 has a negative sign, right? So I have a negative sign here. And then 1 0, 1 0 here, 1 0 there, and 1 0 here. So actually 0 0. Yeah, that's 0 0. Okay, so 1 1. Now 1 1 is beta 0, beta 1, and then minus alpha 1, beta 0, 1 1. Okay, so you can go for one part, but let's now assume that we rate c equals to 0. Okay. Okay, so maybe I can erase this part. Better to erase this part. So in this case, your data qubit is initialized as this. Okay. So that's can you make it a little bit cleaner? So what is it? Alpha 0. Let me do it as far as I can. So alpha 1 beta 1 0 and alpha 1. Maybe that's not the good way to do this. So let's see. Is there any other clever way of doing this? So in other words, can you make it into a tensor product of 2 qubits? So here you can see that this one is equal to this one, right? And this one is equals to this one, right? So let's do that. So we have alpha 0, alpha 1 plus alpha 0, beta 1, 0, 0 plus 1, 0, and alpha 1, beta 0 minus beta 0, beta 1, and 0, 1 plus 1, 1. So whenever we do this calculation, we must not forget that our plus and minus have a coefficient 1 over square root of 2. So overall, since we applied those Hadamard twice, we have 1 over 2 as a coefficient. Okay, so just think about this 1 over 2 all the time. Okay, so we're not really care about this, the exact coefficient. We only need to know whether the data qubits is initialized at the eigenstate. So let's do a little bit one more computation with this one, and plus times 0, and this one plus, here we had plus times 1. Let's see, can I do one more? So can I do one more step? Can I combine something here? So maybe I can combine plus state here, right? So plus times what? So here plus, so let's not worry too much about this coefficient because I get confused. So we have just we have 1 over 2 erased here. And now this coefficient multiplied here. So alpha 0, alpha 1, alpha 0, beta 1, 0, and then plus alpha 1, beta 0, beta 0, beta 1, 1. Okay, so this is the qubit 1, and this is the quantum state of qubit 0. So we read the C0, and the case is you can get a 0 whenever if you have your data qubits. So there are two possibilities. So suppose that you don't have a Z syndrome measurement and you got 0. That means you have plus 1 eigenstate of X syndrome measurement, right, on the qubit 1. And suppose that we don't have X syndrome measurement here and you got C0, then you have plus 1 eigenstate for the data qubit 0, right, on the Z syndrome measurement. But now you kind of combine together, right? But you got the C0. So the case is either these two have plus 1 eigenstate of X syndrome measurement and Z syndrome measurement, or it could have -1, -1 eigenstate for X syndrome measurement and Z syndrome measurement. So there are two possibilities, right? So look at this first one, Q1. So I hope the computation is correct. So we have a +1. It should have a minus. So it has to be something like plus times 0 something, so something here, and minus times 1. So let me see something is missing here. So let's see. So let's see psi 2, right? Psi 2, psi 3, and psi 4, psi 4. So we got this, right? So we got these. And after taking a syndrome measurement, if you get 0, now I want to combine these two. So I'm actually looking for any mistake I made here. Let's see. Psi 0 is okay. Psi 0 is okay. And psi 2 is okay. Okay, so I just change this and change this, and this part minus and minus, right? And yes. Okay. So yeah. Okay. So I think I made a mistake here. So we apply that gate on the 0 qubit, right? So on psi 3, I should look for. No, it's right. No, it's right. Look for ones in the rightmost part. Yes. So I might put the minus part here, minus part here. Here. Oh, here minus. Oh, okay. So it's, let's see. Oh, okay. Yes, they have a different sign, right? So thank you very much. So we have minus here, and then what? Yes. So then now we have minus here. Now minus. Okay. Yeah. Great. So we have what? So it's not an entangled state. It's an entangled state, but I mean, depending on the coefficient, initial coefficient, it could or could not. But anyway, we have superposed state of these two quantum states. And look at this one. As I said, this plus ket state is for the qubit 1, and it's +1 eigenstate of X gate, right? +1 eigenstate. And then 0 ket is the quantum state of the qubit 0, and it's the +1 eigenstate of Z gate. So if this was the case, let's say this, I mean, the quantum state is coexisting together, but suppose that our base state, just one base state here, if this was the case, then we get a +1 eigenstate, therefore the individual measurement will give you 0, 0, but therefore it's a 0. But here, there's another case which gives you -1 eigenstate and -1 eigenstate. So therefore, it also gives you overall the 0 outcome, measurement outcome, because -1 times -1 gives you +1. So you have these quantum states. Of course, we don't know exactly what the coefficients are, but this is +1 eigenstate of x1 z0. Okay. So you don't have to initialize it first. You have to take a measurement, and then by the measurement, you kind of initialize your data qubit into eigenstate. But you don't know which eigenstate it is. So it could be +1 +1 or -1 or -1 in this case. But the important fact is it's just an eigenstate. And this eigenstate is kind of one-to-one mapping with our this footprint. So if it was, let's say 0, 0, 0, 0 all the way here. If it's 0, 0, 0, 0, it means that the 5-qubit state is initialized as a plus 1 eigenstate for these 4 gates, and it's not just a single base state. It could be lots of superposition of lots of other base state, but the important fact is just it is initialized as eigenstate. And you might ask, okay, so if I just randomize this initial state and then just read off something here, then I know that the data qubit is initialized as an eigenstate. But what if it's not read off as 0, 0, 0, 0? What if it's not at 0, 0, 0, 0? Let's say, what if it's 1, 1, 1, 1? What if you read 1, 1, 1, 1 in that case? Because there's 2 chances, right? So if you read 0, you got this. You could also read 1, right? I'm not saying you always get 0. You can get 1. There's probability of getting 1. Unless, I mean, the read off is always there are only 2 there are 2 choices unless your base data qubit is initialized as an eigenstate, right? So if you read 1, 1, 1, 1 instead, then you just start that state as your initial state. You don't have to go for 0, 0, 0, 0. Just start with 0, 0, 0, 1, 1, 1, 1, 1, and then run the circuit, and then take the error detection and see when the error is occurred by looking at the changing of your timestamp, your footprints here. So suppose that you have, so in that case, you can see that you can consider 1, 1, 1 here, 1 on each measurement outcome to be switched to 0, and 0 is also switched to 1. So you're kind of now taking 1 as if it's 0 in our original table, and then 1 as a 0 and as 1. You just look for when 1 is changed to 0 and 0 is changed to 1. See what I'm saying? This kind of could be confusing, so let me write it down. Detail here. So the question is, what if the read off? So read off means C0, C1, C2, C3 is not 0, 0, 0, 0. But how do we proceed? So suppose initial read off is 1, 1, 1, 1. Well, that's also real chance, so maybe it's better to say, okay, so 1, 0, 1, 0. Okay, I got this state. So, and if you see the table, I've erased the half of them. So, just if you think about this case, then you can see whether it's a plus or minus eigenstate of this measurement M0 to M3. But that's not important. I can just say, let's say this is C0, C3. So change interchange 0 and 1 in the table in the row of the table corresponding M0 and M2. See? So here, M0, this one is M0, right? So this one, M0 here, and M2 here. So since our initial state was 1, 1, 1, 1 and 1, this is now our starting point. We want to see whether error occurred. So when error occurred, it changes the state. It changes the eigenvalue of the eigenstate. So whenever the eigenvalue is changed, we can detect it by change of the readoff, right? It's the change that is important. It's not like absolute value indicates the eigenvalue of the eigenstate, but the error detection is detecting the change of eigenvalue, in other words, change of your readoff. So we don't have to go for the confusing 1, 0, 1, 0. Just interchange the role of 1 and 0 for these two cases on the first row and the third row, right? Then you can just use the same table. So it really doesn't matter. So there's two things. Doesn't matter whether you initialize your data qubit in an initialization process of your quantum error correction into zero cats, and you don't have to initialize every time until you get 0, 0, 0, 0. Just take a one initialization step and then start from whatever you got. And then if it gets confusing, then you can just change the table itself and take the new table as error detection method. Okay? That makes sense? The best way to learn this is just make your own simulator of your error correction. So I don't think we can have time to go for the logical qubit and 7-qubit error correction code. We're gonna cover it next time, and probably we start surface code next week.